In 1991, a cosmic ray detector in Utah recorded something that should not exist. A single subatomic particle, smaller than an atom, carrying no electric charge that would explain its behavior, arrived at Earth's upper atmosphere traveling at 99.99999999999999999999999999999999999999999999999999999999999999999999999999999 of the speed of light. Write that out and count the nines, 22 of them after the decimal point. A particle moving so close to the speed of light that the difference between its velocity and the speed of light is smaller than any number that has a name in ordinary language. The particle carried energy equivalent to a baseball traveling at approximately 90 kilometers per hour. That sounds unremarkable until you understand that a baseball is made of roughly 10 to the 25th power atoms, 10 million billion atoms. This particle was a single subatomic particle, one, carrying the kinetic energy of a macroscopic object moving at highway speed. It was given a name that the physicists who discovered it chose with the specific intention of conveying how they felt about it. They called it the "oh my God" particle. And the reason it breaks physics is not just its energy, it is that according to the laws of physics as we understand them, it cannot exist. It cannot have traveled far enough to reach us. The universe itself should have stopped it long before it arrived. It arrived anyway. To understand why the "oh my God" particle is impossible, you need to understand something called the GZK limit. In 1966, 25 years before the Utah detection, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently calculated a theoretical upper limit on the energy of cosmic rays that could travel through the universe. Their reasoning was elegant and disturbing. The universe is not empty. It is filled with the cosmic microwave background radiation, the afterglow of the Big Bang, a bath of low-energy photons permeating every cubic centimeter of space in every direction. These photons are cold and carry almost no energy individually. They're effectively invisible to everything except the most energetic particles in the universe. For a particle traveling at close to the speed of light with sufficient energy, those cold photons are not invisible. Due to relativistic effects, the way energy and momentum transform at velocities approaching the speed of light, what appears to be a cold, low-energy photon in the reference frame of the universe appears as a high-energy gamma ray in the reference frame of the particle. And at high enough energies, that interaction produces a reaction. The cosmic ray particle collides with the background photon and produces new particles, losing energy in the process. This happens continuously. Every interaction strips energy from the cosmic ray. A proton traveling above approximately 5 × 10 to the 19th electron volts, the GZK limit, loses energy so rapidly through these interactions that it cannot travel more than roughly 160 million light-years before its energy drops below the threshold. The "oh my God" particle carried an energy of 3 × 10 to the 20th electron volts, 6 times the GZK limit. At that energy, a proton crossing the cosmic microwave background loses energy so quickly that it could not have originated from more than 50 to 100 million light-years, a relatively small distance in cosmological terms. There are no obvious sources of particles at that energy within that distance, no known astrophysical object in our cosmic neighborhood capable of accelerating a proton to that velocity. The particle came from somewhere. It carried energy that physics says it should have lost before it could travel far enough to reach us, and it arrived at a detector in Utah on the 15th of October 1991 and was recorded. The immediate response from the physics community was to look for the error. Cosmic ray detectors do not directly observe the primary particle. What they observe is the cascade of secondary particles produced when the primary cosmic ray strikes a molecule in Earth's upper atmosphere, an air shower, a cone of billions of secondary particles spreading downward through the atmosphere and arriving at ground-level detectors spread across a large area. From the pattern of the air shower, which detectors were hit, in what sequence, with what intensity, physicists reconstruct the properties of the primary particle. The reconstruction is indirect. It involves models of how air showers develop and how secondary particles behave in the atmosphere. Maybe the model was wrong. Maybe the energy reconstruction overestimated the primary particle's energy. Maybe what looked like a 3 × 10 to the 20th electron-volt proton was actually something more modest, an artifact of a model that did not correctly describe an unusual shower. Physicists spent years examining the reconstruction. They found no significant error. The energy estimate held up under scrutiny. Then, in 2002, a larger detector array called high-res confirmed the GZK cutoff. It found evidence that the cosmic ray spectrum did indeed show a suppression at energies around the GZK limit, consistent with the theoretical prediction. The cutoff was real. The oh my god particle was above it. Then, in 2008, the Pierre Auger Observatory in Argentina, the largest cosmic ray detector ever built, covering 3,000 square kilometers of the Pampas, began publishing results. It found cosmic rays above the GZK limit, multiple events, not one anomaly, but a population of anomalies, arriving at a rate that, while rare, was statistically robust. The oh my god particle was not a mistake. It was the most extreme example of something real. So where do they come from? The leading explanation involves the most powerful astrophysical accelerators known to exist, active galactic nuclei, the supermassive black holes at the centers of certain galaxies that are actively consuming material and launching jets of plasma at close to the speed of light. The jets of active galactic nuclei are the most energetic, continuous phenomena in the observable universe. They can extend for millions of light years. Along their length, shock waves and magnetic fields accelerate particles to extraordinary energies through a process called Fermi acceleration, particles bouncing repeatedly across a shock wave, gaining energy with each crossing, like a ball bounced between two approaching walls. Active galactic nuclei can, in principle, accelerate particles to approaching the GZK limit. The question is whether they can reach the energies of the oh my god particle, 6 times above it, and whether any active galactic nucleus lies within the 100 million light-year radius from which such a particle could reach us.
The Pierre Auger Observatory attempted to answer this by searching for correlations between the arrival directions of ultra-high energy cosmic rays and the positions of known active galactic nuclei. They found a statistical correlation: more cosmic rays arriving from directions consistent with nearby active galactic nuclei than would be expected by chance. But the correlation is imperfect. Not all ultra-high energy events point back to an obvious source. The oh my god particle's arrival direction, traced back across space, does not point unambiguously at a known active galactic nucleus or any other obvious candidate source. The particle arrived. We do not know where it came from. But here is where the physics becomes genuinely strange. The GZK limit is not the only law that ultra-high energy cosmic rays appear to challenge. Special relativity has a property called Lorentz invariance, the principle that the laws of physics are the same in all inertial reference frames, regardless of relative motion. This is one of the foundational principles of modern physics. Every experiment ever designed to test it has confirmed it. But at the energies of the oh my god particle, some theoretical frameworks predict that Lorentz invariance might break down. Quantum gravity theories, the attempts to reconcile general relativity with quantum mechanics, sometimes predict that at the Planck scale, the finest scale of space-time itself, the smooth, continuous fabric of space and time assumed by relativity might be replaced by something granular, something foamy, something that introduces tiny deviations from perfect Lorentz invariance. Those deviations would be undetectable at ordinary energies, but a particle at 3 × 10 to the 20th electron volts is not at ordinary energies. It is at the highest energies ever recorded in any particle anywhere. At those energies, even a tiny deviation from Lorentz invariance could have measurable consequences.
Some physicists have proposed that the Oh My Dad particle's ability to exceed the GZK limit, to carry energy that should have been stripped away by interactions with the cosmic microwave background, might be explained by a violation of Lorentz invariance. If the interaction between the cosmic ray and the background photons is slightly different from what perfect Lorentz invariance predicts, the GZK energy loss could be reduced, allowing the particle to travel further and arrive with higher energy than the standard calculation allows. This explanation is speculative. Lorentz invariance has never been shown to break down in any experiment. The standard calculation may simply have underestimated our uncertainty about the source, or our models of the source environment may be incomplete. But the possibility that the Oh My God particle is showing us, in the most extreme conditions ever measured, a crack in one of the most fundamental principles of physics, that is not a possibility that can be dismissed without evidence. The Oh My God particle is the most extreme, but it is not alone in the category of things that arrive from the universe and do not behave the way physics predicts. In 2016, the ANITA experiment, a radio detector flown on a balloon over Antarctica designed to detect the radio emission from cosmic ray air showers, recorded two anomalous events. Radio pulses arriving from below the horizon, from inside the Earth, at angles that indicated a source beneath the surface. Cosmic ray particles do not travel through the Earth. The planet is opaque to them. A particle arriving from below the horizon, from within the Earth, is a particle that passed through thousands of kilometers of rock, which is impossible for the known particles that ANITA was designed to detect. The standard model of particle physics has no particle that would survive transit through the Earth at the energies ANITA measured. The events were inconsistent with any known particle traveling in any known way. Proposed explanations included sterile neutrinos, a hypothetical particle that interacts so weakly with normal matter that it could pass through the Earth without scattering. Others proposed supersymmetrical particles, a whole class of hypothetical particles predicted by extensions of the standard model, but never detected. Others suggested the events were simply background artifacts, explained by known physics in ways not yet fully worked out. The ANITA events remain unexplained. A follow-up analysis has not identified a convincing standard model explanation. The collaboration that reported them has not retracted the results. Two particles arriving from inside the Earth with no known explanation. And then there is the muon anomaly. The muon is a particle like an electron, but 200 times heavier. In high-energy collisions, the kind produced in particle accelerators, collisions produce a characteristic ratio of muons to other particles that the standard model predicts with high precision. In cosmic ray air showers, the same collisions occur in the upper atmosphere, and the muon production rate in cosmic ray air showers is consistently higher than the standard model predicts. Not by a tiny amount, by a factor of roughly 30 to 80% above the predicted rate, depending on the energy range and the analysis method. The muon puzzle in cosmic ray physics has been known since the 1990s. Multiple experiments across multiple decades have confirmed it. The standard model of particle physics, the most precisely tested theoretical framework in the history of science, predicts the wrong number of muons in cosmic ray showers. Something is producing extra muons in the upper atmosphere, something that the standard model does not include.
We do not know what. Here is the picture that emerges when you put all of this together. A particle arrives with energy 6 times above the theoretical maximum for particles that could have traveled far enough to reach us. A radio detector in Antarctica records pulses arriving from inside the Earth with no known explanation. Cosmic ray air showers consistently produce more muons than the best available theory predicts. These are not the same phenomenon. They involve different particles, different detectors, different physics. They do not necessarily share a common explanation, but they share a common character. They are observations made at the most extreme energies accessible to experiment, energies where our theories are being tested in regimes they were never designed for, and they do not fully fit. The Standard Model of particle physics is the most precisely tested theory in the history of science. Its predictions have been confirmed to extraordinary accuracy across decades of experiments. When it is wrong by 30%, consistently, reproducibly across multiple independent experiments, that is not a rounding error. That is a signal. When a particle arrives carrying energy it should not have been able to carry, that is not instrumentation noise. It is a measurement. The universe is telling us something at these energies. It is showing us the place where our best description of reality begins to fail. Not catastrophically. The Standard Model still explains almost everything. But at the edges, at the highest energies, in the most extreme conditions, something is there that the theory does not contain. The history of physics is a history of boundaries. Newtonian mechanics was the most successful physical theory ever constructed until it was tested at velocities approaching the speed of light and failed. Special relativity replaced it at high velocities. Classical electromagnetism explained everything about light and electricity until it was tested at the scale of atoms and produced predictions that were catastrophically wrong. Quantum mechanics replaced it at small scales. Every time physics reached a boundary, every time the theory was tested in a regime it was not designed for, what was found at the boundary was not a failure of reality. It was a deeper layer of reality, a more complete description waiting underneath the one we had. The oh my god particle is a boundary marker. The Anita events are boundary markers. The muon anomaly is a boundary marker. They are measurements taken at energies where our current description of particle physics is showing its limits. What lies beyond those limits, we do not know. Supersymmetry, extra dimensions, a modified understanding of Lorentz invariance, something not yet proposed, not yet named, waiting for the experimental evidence that forces it into existence the way quantum mechanics was forced into existence by the failures of classical physics. The oh my god particle traveled across the universe at 99% of the speed of light. It arrived in Utah. It was recorded. And then it was gone. Absorbed in the atmosphere, its energy dispersed into a cascade of secondary particles that spread across the desert and triggered an array of detectors that had been waiting patiently for something they did not expect. For one moment, the most energetic particle ever detected struck our atmosphere and left its signature in the data. It carried a message from the edge of what physics understands. We are still reading it.